I apologize that my voice isn't the best today. I'm still recovering from a cold. But we're going to switch to chapter 3 today. So hopefully chapter 3 isn't anything that new for you guys. You guys have all seen acid-base chemistry before in your other chemistry classes. But I'm going to present it in a little bit different way than what you've seen before. So let's do a little bit of review. Originally, acid-base theories developed in 1923. And there were two different competing sets of theories. The first one was created by two chemists, Bronsted and Lowry. And then the second one was made by our good friend Gilbert Lewis, the guy who got passed up for the Nobel Prize 35 different times. So two competing theories. Both of them are correct in their own ways, and we're going to talk about each of them in a fair amount of detail. But first, let's start with Bronsted and Lowry. Does anybody remember what the Bronsted-Lowry acid-base theory was? Yeah, I heard somebody say it. You were saying acid is something that gives up a hydrogen ion. A base is something that accepts it. What ion are we talking about? Is it a cation, an anion? Cation. So we call them protons typically. Hydrogen cation is referred to as a proton. And acids donate protons. And bases accept protons. Pretty straightforward theory. So let's take a look at this in terms of chemical reaction. So let's say we've got our acid HA. And I'm going to draw our acid in red. And we've got another base, and I'm going to draw this base in green. And essentially all that happens is that the proton that's attached to our acid gets handed off to our base. The way I always imagine this is like a track relay, where our proton is a baton. And we're handing it off from our acid to our base. So our acid, if it loses its proton, now becomes negative. And our base, if it accepts a proton, is going to become positive. So we can clearly identify this is our acid because it gave up our proton. This is our base because it accepted our proton. What do we call A minus? It's an anion, yeah. But now it could act as a base, right? Because it lost its proton, it could accept it back. So we call this a conjugate base. And this would be our conjugate acid. And you may have noticed that instead of using a one-way arrow, I actually used an equilibrium arrow. We're going to talk quite a bit about this equilibrium arrow, but it's important to remember that an acid on the left-hand side gave up its proton, but now on the right-hand side we have a conjugate acid. This could alternately give it back and shuttle the reaction left and right and left and right and left and right. So in reality, there's an equilibrium occurring. But there's one other important thing that I did want to talk about. If we've got a strong acid, what does that mean about our conjugate base? Yeah, exactly. So strong acids form stable, spelled form wrong. Stable or weak conjugate bases. And strong bases form stable or weak conjugate acids. So right now we're writing things out in pretty generic terms, but If we use a really, really strong acid like HCl, that means its conjugate base is going to be the chloride anion. That's a really weak base. It's pretty stable. It's happy on its own. So by definition, HCl is going to be a strong acid. And we can use this to comparatively assess whether or not an acid is strong or weak. We're going to spend a lot of time talking about this, but let's take a step back and talk about the equilibrium that's occurring here. Oh, let's actually put this in the first section. So let's define our equilibrium. Uh-oh. Come on. So let's rewrite this, and I'm going to write it instead using our generic acid HA, and we're going to put this into water. Water is our universal solvent. And if we do this, what will our conjugate acid be? Hydronium ion, right. So we get H3O plus because water accepted a proton. And then we'd end up with our conjugate base, and I'll call this A minus. So this is our generic acid-base equilibrium in water. So how many of you guys remember KEQ? Equilibrium constants, right? This is Chem 163, I believe you guys covered this. So what does the KEQ represent? Yeah, products over reactants. So it's a concentration of our products, which is H3O plus, and our conjugate base, A minus, over our reactants, which is HA and H2O. And what chemists do oftentimes is this concentration of water, because it's the bulk solvent, usually is relatively unchanged during the reaction. And so we turn this into a constant. And so I'm going to rewrite this a little bit differently and pull out that H2O expression over on the left-hand side. So now we've still got hydronium on the top and our conjugate base on the top. But now on the bottom we just have HA. So we're treating water, the concentration of water, more or less as a constant. Let me slide this down a bit. And what we call this is Ka. Oops. So Ka just refers to this entire portion of our equation right here. So it's directly related to our equilibrium constant, right? What does it mean if Ka is large? What does that say about our acid? It's strong, right? If Ka is like 100 billion, that means we've got a lot of hydronium in solution, right? The numerator is very, very big. If Ka is very, very tiny, that means we've got very, very little hydronium in solution. That means our acid's weak. So we can comparatively look at this and we can say large Ka equals strong acid, and small Ka equals a weak acid. Okay, so let's take a look at some examples with these acids and bases. Yep.
So the K equilibrium is products over reactants.
Yep.
But I'm sorry, why did you take out the H2O?
Because H2O is our bulk solvent in this reaction. The concentration of our solvent is more or less constant. And so we treat it as a constant by pulling it out over onto the KEQ side. And so now KEQ times our concentration of water, we just refer to that as Ka, because both of those should be constants. Yeah. Yep.
When you took out the liquid, does that also go for solids?
Yeah, normally with acid-base chemistry and organic chemistry, we're referring to everything in liquid phase, but normally when we are looking at these, you're looking at concentration, which implies liquid. Yep. Okay, so let's take a look at some examples. All right, example 1, I've got HCl, and I'm going to combine this with H2O. This is in equilibrium with our chloride ion, which is Cl minus, plus our hydronium ion, which is H3O plus. All right, so let's write out Ka. So Ka is going to be equal to our concentration of chloride times our concentration of hydronium divided by our concentration of HCl. I know a lot of you mentioned that you got really good at doing titrations last year. These values are all determined experimentally. There's been a lot of effort to try to solve these computationally. It's not that easy. Oftentimes you actually have to have a person go out and check the equilibrium. And so if you do this, you can solve for Ka. And the Ka for this equation is 100 million. Pretty large number, right? Let's compare a separate example. But before we go on to our next example, do you think 100 million qualifies as a large number? Yeah, so it's probably going to be a strong acid. HCl is generally considered to be a fairly strong acid. All right, let's do a separate example. Let's take methane plus water. And again, we'll consider methane to act like our acid in this case. So if methane loses a proton, it's going to be CH3 with a lone pair and a formal negative charge. And then we've got our hydronium ion. Okay, so let's write out our Ka expression here. We've got our conjugate base, which is CH3 lone pair with a negative charge, times our concentration of hydronium ion over our concentration of CH4, or methane.
So you're just saying that H2O is a constant?
Yeah, remember, we said we're treating H2O as a constant, and that constant becomes a part of the Ka portion of our equation. Yep. So now we can determine this somewhat experimentally. This becomes a little bit more challenging. And the Ka for this equals 0.00000000000000000. If we go through and we actually count all the zeros in here, there's 48 zeros. The probability of this reaction occurring is less than the probability of you finding one distinct atom in the known universe. It's incredibly small. The equilibrium in this case practically doesn't exist. We would say that you're never going to see this reaction go forward on the right-hand side, which means that CH4 is considered an incredibly weak acid. So as you can see, we're running into a problem where we're having to write out a lot of zeros. What's the solution to our problem with the zeros? Oh, I heard scientific notation. We could do that. We could write 10 to the negative blah, 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 blah. But there's an even easier way.
Just write zero.
Just write zero. Just round. Does anybody remember pKa's? Oh, yeah, pKa's. So chemists use pKa's Does anybody remember what P in the pKa stands for? It's a mathematical operator, but what does the P mean? Negative log, yeah. So pKa equals negative log of Ka. So if we go through and we do negative log of 100 million, that means that its pKa is going to be 8. Or sorry, -8. I forgot the negative there. That's a lot easier to write than 100 million. And if we go over here and we say, all right, pKa of the one with 48 zeros, we can write that as a pKa of 48. So really we're just counting how many digits, or let me rephrase that. We're basically counting the exponent there, right? So in this one, we're going to the -48. We cancel out the negative. It becomes +48. So if we look at this, small pKa's, does that equal a strong acid or a weak acid? Strong acid. And a large pKa, meaning something about 50, is a weak acid. So typically the range we see in organic chemistry ranges from about -10 to about 50. That's a nice manageable range. It's a lot easier than the ranges for Kas. All right, so for your problem of the day, I want you to look at the acids that I gave you, and I specifically want you to imagine what the conjugate base would look like and what could potentially stabilize the conjugate base for the two molecules. They're very, very similar. All right, if you guys have questions, feel free to stop by my office tomorrow.